Implementation of Smart Energy Systems by 2026, a comprehensive overview. Introduction. The transition to smart energy systems by 2026 represents a significant advancement in the way energy is managed, focusing heavily on applications of Internet of Things (IoT) technology and artificial intelligence (AI) analytics. With an investment plan totaling $5 million, the initiative is poised to enhance energy efficiency, minimize waste, and optimize consumption across various sectors. This report outlines the critical phases of implementation, the technological integrations involved, and the anticipated outcomes of this strategic initiative. Phase 1: Initial Assessment and Pilot Programs. Objective. The first phase involves an initial assessment of existing energy systems and the establishment of pilot programs. These programs will serve as testbeds for implementing IoT devices and AI analytics. Activities. 1. Assessment of current infrastructure, auditing existing energy systems to identify inefficiencies and potential areas for improvement. 2. Pilot project selection, selecting specific locations or systems for pilot implementations. Focusing on diverse energy environments such as residential, commercial, and industrial sectors. 3. IoT device installation, deploying IoT sensors and devices to gather real-time data on energy consumption, production, and other relevant metrics. For AI analytics development, developing AI algorithms to analyze the data collected, focusing on predictive analytics to forecast energy demand and identify patterns. Expected outcomes. Validation of IoT technology in real-world applications. Initial insights into data analytics capabilities and their impact on energy management. Phase 2: Full-scale implementation. Objective. Upon successful pilot testing, the second phase will roll out the full-scale implementation of smart energy systems across all identified sectors. Activities. 1. System integration, integrating IoT devices with existing energy management systems to create a cohesive network. 2. AI model training, training AI models on the data gathered during pilot programs to enhance predictive accuracy and operational efficiency. 3. User training and engagement, conducting training sessions for end users and stakeholders to ensure smooth adoption of the new systems. Expected outcomes. Enhanced energy management capabilities through real-time data analysis. Improved operational efficiencies and reduced energy costs. Increased user engagement and awareness of energy-saving practices. Phase 3: Optimization and Scaling. Objective. This phase focuses on optimizing the performance of the smart energy systems and scaling the solutions to broader geographical areas. Activities. 1. Performance monitoring, continuously monitoring the performance of the installed systems using AI analytics to identify areas for improvement. 2. Feedback loop creation, establishing a feedback mechanism to gather user experiences and suggestions for further enhancements. 3. Scaling solutions, expanding the reach of smart energy systems to additional locations. Leveraging lessons learned from initial implementations. Expected outcomes. Continuous improvement of energy management practices. Broader adoption of smart energy systems leading to increased energy savings across regions. Phase 4: Evaluation and future projections. Objective. The final phase involves a comprehensive evaluation of the entire initiative and planning for future enhancements and technologies. Activities. 1. Data analysis, analyzing the data collected over the implementation period to assess the impact on energy efficiency and cost savings. 2. Stakeholder review, engaging stakeholders in a review process to discuss outcomes, challenges, and future opportunities. 3. Long-term planning, developing a strategic plan for integrating emerging technologies and innovations in energy management. Expected outcomes. Detailed report on the effectiveness of smart energy systems. Strategic roadmap for ongoing improvement and adaptation of new technologies in energy management. Technological integration, IoT and AI. IoT integration. The backbone of the smart energy systems will be built on IoT devices that provide real-time monitoring of energy usage. These devices will facilitate data collection from various sources including smart meters, sensors, and appliances, allowing for a comprehensive understanding of energy consumption patterns. AI analytics. AI plays a critical role in analyzing the vast amounts of data collected from IoT devices. By employing machine learning algorithms, the system can offer predictive insights, optimize energy distribution, and automate energy-saving measures. This synergy between IoT and AI is essential for achieving real-time energy management. Common key points. 1. Emphasis on efficiency. A recurring theme across all phases of implementation is the focus on enhancing energy efficiency and reducing operational costs. Organizations adopting these technologies report significant improvements. 2. Cautious optimism. While the potential ROI and transformational benefits of smart energy systems are highlighted, there is a recognition of the challenges posed by the trough of disillusionment, where early adopters may experience performance issues and lower than expected ROI. 3. Diverse applications. The initiative recognizes the applicability of smart energy systems across various sectors, including residential, commercial, and industrial settings, each with unique challenges and opportunities. Conclusion. The implementation of smart energy systems by 2026 is a multi-phase initiative that aims to revolutionize energy management through the integration of IoT and AI technologies. With a strategic investment of $5 million. This initiative has the potential to significantly enhance energy efficiency, reduce costs, and foster sustainability across various sectors. As the project progresses, ongoing evaluation and adaptation will be crucial to ensure its success and relevance in an evolving technological landscape. Through careful planning and execution, organizations will not only improve their energy management practices but also contribute to broader environmental and economic goals. The content provided discusses the implementation of smart energy systems by 2026 with a significant focus on IoT integration and AI analytics for real-time energy management. Here I'll address the counterintuitive information within the context of this initiative. 1. Investment perception. One could assume that a $5 million investment in technology like IoT and AI is substantial given the high costs of advanced technologies. However, in the wider context of energy management and smart grid technologies, $5 million might be seen as a relatively modest sum. This contrast between the perceived adequacy of the investment and the potentially vast scale of infrastructure needed for a smart energy system is counterintuitive. It suggests that while small investments can catalyze change, they may not be sufficient for comprehensive implementation. 2. Expected ROI versus skepticism. There's a clear divide in perspectives regarding the return on investment ROI for such technologies. While many sources highlight significant long-term benefits from implementing IoT and AI for energy management, some experts express skepticism, cautioning about the trough of disillusionment as outlined in Gartner's hype cycle. The expectation of rapid ROI conflicts with the reality that many organizations may encounter setbacks or slower adoption rates as they navigate the complexities of new technologies. This disconnect between the enthusiasm for immediate benefits and the cautionary tales of slow adoption reflects a counterintuitive understanding of technological integration in traditional sectors. 3. Efficiency gains versus implementation challenges. The narrative emphasizes that organizations adopting IoT and AI technologies have seen substantial efficiency improvements and cost reductions. However, it fails to thoroughly address the significant challenges these organizations face during implementation, including resistance to change, the need for employee retraining, and the complexities of integrating new systems with existing infrastructure. The expectation that technology will seamlessly enhance efficiency overlooks the fact that the path to such improvements often requires overcoming substantial hurdles. making the relationship between technological adoption and operational efficiency much less straightforward than it appears. 4. AI and IoT synergy. The content suggests that the integration of AI and IoT will naturally lead to smarter energy systems, implying a seamless synergy. However, the reality is that integrating these technologies can be fraught with difficulties. The need for interoperability among various devices' data standards and protocols can create significant roadblocks. The assumption that technological advancements will lead to immediate synergies contradicts the complex nature of system integration, where many companies struggle to achieve the promised benefits of AI and IoT cooperation. 5. Pilot projects versus immediate rollout. The plan anticipates pilot projects as a starting point for broader implementation. This approach is often lauded as a best practice, allowing organizations to test and refine their technologies. However, the counterintuitive aspect is that pilot projects can also lead to analysis paralysis, where organizations become so focused on testing that they delay broader adoption. The expectation that pilot projects will lead quickly to scaling can be misleading, as they may instead create a scenario where companies remain in a testing phase longer than intended, thus delaying the overall benefits of smart energy systems. 6. Industry-wide adoption. There is an underlying assumption that if a few organizations successfully adopt these technologies, it will lead to widespread industry adoption. However, the truth is that successful case studies do not guarantee that other organizations will follow suit. Factors such as different organizational cultures, varying levels of technological maturity, and the unique requirements of different sectors can lead to uneven adoption rates. This assumption about the ripple effect of successful implementations contradicts the complex landscape of organizational behavior and technology adoption. 7. Public versus private sector dynamics. The narrative primarily focuses on private sector investments and advancements in smart energy systems. However, the counterintuitive element here is the potential role of public sector initiatives. Often the public sector can act as a catalyst for technological adoption through regulations, incentives, and funding. The expectation that private investment alone will drive the transition to smart energy systems overlooks the significant influence that public policy and government funding can exert on these initiatives. In summary, the detailed exploration of smart energy systems by 2026 reveals several counterintuitive insights about investment perceptions, expected ROI, efficiency gains, technological synergy, pilot projects, industry-wide adoption, and the dynamics between public and private sectors. These elements highlight the complexities and challenges inherent in the integration of advanced technologies within traditional energy systems, suggesting that while the potential for innovation is significant, the path to realization is often fraught with unexpected hurdles. The report detailing the implementation of smart energy systems by 2026 emphasizes several critical aspects that, while mentioned, are often overlooked or inadequately understood by many stakeholders. Here are some significant elements that deserve more attention, along with explanations of their significance. 1. Phased implementation approach. The report outlines a structured, phased approach to the implementation of smart energy systems. While many may focus on the anticipated technologies such as IoT and AI, the significance of this phased approach is crucial. Implementing complex systems in stages allows for iterative learning, risk management, and scalability. It enables organizations to test and validate technologies in pilot projects, adjust strategies based on real-world data, and gradually scale up operations. This adaptive approach reduces the risk of large-scale failures and optimizes resource allocation. 2. Interoperability among devices. The integration of IoT devices is highlighted, yet the underlying aspect of interoperability is often overlooked. Ensuring that various devices and systems can communicate seamlessly is essential for the success of any smart energy initiative. Interoperability allows for a more cohesive energy management system where data from different sources can be aggregated and analyzed effectively. This capability is significant because it enhances the overall efficiency of energy consumption and facilitates the development of more advanced AI analytics that can generate actionable insights. 3. AI-driven predictive analytics. The report mentions AI analytics but may not fully convey the transformative potential of predictive analytics in energy management. This technology enables organizations to forecast energy demand, detect anomalies, and optimize energy distribution proactively. The significance of predictive analytics lies in its ability to enhance decision-making processes, resulting in improved energy efficiency and cost savings. By anticipating issues before they escalate, organizations can avoid outages, reduce maintenance costs, and enhance customer satisfaction. 4. Return on investment (ROI) beyond financial metrics. While many stakeholders may focus on immediate financial returns from the $5 million investment, the broader implications of ROI in terms of sustainability, regulatory compliance, and corporate social responsibility are frequently understated. The transition to smart energy systems represents not only a financial investment but also a commitment to environmental stewardship and innovation. This dual focus can enhance brand reputation, meet regulatory expectations, and ultimately lead to long-term financial benefits as energy markets continue to evolve toward sustainability. 5. User engagement and behavior change. The report discusses technology integration but may underemphasize the importance of user engagement and behavioral changes necessary for the successful adoption of smart energy systems. Engaging end users through education and incentivization is vital for achieving desired energy efficiency outcomes. Understanding user behavior preferences and barriers to adoption will inform the design of systems and policies that encourage proactive participation in energy management. This engagement is significant because it drives the success of technology deployment and ensures that solutions are user-centric and effective. 6. Regulatory and policy frameworks. The report briefly mentions the role of frameworks but does not elaborate on how existing regulations may impact the implementation of smart energy systems. Understanding the regulatory landscape is essential for stakeholders to navigate compliance challenges and to leverage incentives for technological adoption. The significance of this understanding is apparent in how it can shape strategic planning, funding opportunities, and partnerships. Organizations that proactively address regulatory requirements can position themselves as leaders in the energy transition. 7. Socioeconomic impacts. The implications of smart energy systems on job creation, community development, and socioeconomic equity are often overlooked. While the focus is primarily on technological advancements, the broader societal impacts should be highlighted. The deployment of smart energy systems can create new jobs in technology and infrastructure, drive economic development in local communities, and ensure equitable access to energy resources. Recognizing these impacts is significant as it can foster public support and collaboration among various stakeholders, including governments, businesses, and communities. 8. Data security and privacy concerns. As smart energy systems rely heavily on data collection and analytics, concerns regarding data security and user privacy are paramount. The report may not fully address the need for robust security measures to protect sensitive information from cyber threats. The significance of this concern cannot be overstated. Without adequate security protocols, organizations risk data breaches that could undermine public trust and lead to significant financial liabilities. Ensuring data security is essential for the sustainable success of smart energy systems. By focusing on these often overlooked aspects, stakeholders can gain a more comprehensive understanding of the challenges and opportunities associated with the implementation of smart energy systems. Addressing these issues can facilitate a more effective transition to innovative energy management practices, ultimately leading to enhanced efficiency, sustainability, and stakeholder engagement across the energy sector. The implementation of smart energy systems by 2026 with a focus on IoT integration and AI analytics for real-time energy management is a multifaceted initiative that presents significant opportunities and challenges. Here are the 4 most valuable points for in-depth analysis and discussion. 1. Phased implementation strategy. The initiative is structured into distinct phases, allowing for a systematic approach to integration. This phased rollout is crucial for effective adoption as it enables organizations to pilot solutions and gather feedback before broader implementation. Each phase can be tailored based on insights gained, thereby minimizing risks associated with large-scale deployments. This strategy emphasizes the importance of gradual integration, ensuring that all stakeholders are adequately prepared for the transition. 2. Investment in IoT and AI technologies. With a total investment of $5 million, the focus on IoT devices and AI analytics is pivotal. IoT devices will facilitate real-time data collection and monitoring, while AI analytics will process this data to optimize energy usage and distribution. This investment reflects a commitment to leveraging cutting-edge technology to enhance energy efficiency and sustainability. The financial allocation also raises questions about the expected return on investment (ROI) and how success will be measured in terms of energy savings and operational efficiency. 3. Importance of data integration and analytics. The effective integration of data from various sources is paramount for the success of smart energy systems. The collaboration of IoT and AI will enable predictive analytics, which can anticipate energy demands and adjust supply accordingly. This capability is essential for managing energy resources more efficiently, particularly as energy demands fluctuate. The challenge lies in ensuring data accuracy, security, and interoperability among different systems and devices. 4. Skepticism and challenges in scalability. Despite the enthusiasm surrounding smart energy systems, skepticism remains regarding the immediate effectiveness and scalability of these technologies. Some critics point to the trough of disillusionment in technology adoption, where initial excitement gives way to challenges in implementation and realization of benefits. This skepticism highlights the need for robust pilot programs and a clear roadmap that addresses potential scalability issues as systems expand across different sectors. In conclusion, the transition towards smart energy systems by 2026 embodies a comprehensive approach that requires careful planning, significant investment, and a commitment to leveraging technology for enhanced energy management. The phased strategy, investment in technology, effective data integration, and addressing skepticism are critical points that warrant in-depth exploration as organizations embark on this transformative journey. Here are 3 famous historical cases that reflect the themes of technological advancements, energy management, and transformative innovations akin to the content provided. 1. The Manhattan Project, 1942 to 1946. The Manhattan Project was a research and development project during World War II that produced the first nuclear weapons. The project was a massive collaboration involving the United States, the United Kingdom, and Canada, and it brought together some of the greatest scientific minds of the time, including Robert Oppenheimer and Enrico Fermi. The initiative exemplified how focused investment in technology could lead to groundbreaking advancements, changing the course of history and energy management through the introduction of nuclear power. The lessons learned from the Manhattan Project continue to influence energy policy and management, particularly in discussions around sustainable energy sources and the ethical implications of energy technology. 2. The Apollo Program, 1961 to 1972. The Apollo program was a series of space missions conducted by NASA with the goal of landing humans on the Moon and safely returning them to Earth. This initiative not only achieved its primary objective with Apollo 11 in 1969 but also fostered significant technological advancements in various fields, including materials science, telecommunications, and computer technology. The program showcased the potential for government-led investment in technology to drive progress and innovation, leading to new energy solutions and applications in various industries. The cross-disciplinary collaboration and rapid advancements made during the Apollo missions serve as an inspiration for future technological endeavors in energy management and beyond. 3. The electrification of America 1880s to 1930s. The electrification of America was a transformative period in the late 19th and early 20th centuries that saw the widespread adoption of electrical power. This movement was fueled by technological advancements such as Thomas Edison's development of the electric light bulb and Nikola Tesla's contributions to alternating current AC systems. The electrification of homes and industries drastically changed the landscape of energy consumption and management, leading to increased efficiency and productivity. This historical case highlights the impact of integrating new technologies into existing systems and the subsequent evolution of energy management practices. Laying the groundwork for modern smart energy systems and the integration of IoT and AI technologies in managing energy resources more effectively. These historical cases demonstrate how technological innovations can lead to significant shifts in energy management and societal infrastructure, paralleling the contemporary initiatives toward smart energy systems utilizing IoT and AI for real-time management. Future outlook: implementation of smart energy systems by 2026. The implementation of smart energy systems, particularly through the integration of Internet of Things IoT devices and artificial intelligence AI analytics, is expected to significantly transform energy management practices across various industries by 2026. With a planned investment of $5 million, the initiative will unfold in 4 key phases, each designed to progressively enhance operational efficiency, reduce energy waste, and optimize consumption. Here are the predictions for the future of this initiative. 1. Phase 1, Initial Pilot Projects 2024. In the first phase, pilot projects will be rolled out to test the effectiveness of IoT and AI technologies in real-world applications. This phase will focus on small-scale implementations in controlled environments such as commercial buildings and industrial facilities. The primary objectives will be to gather data on system performance, identify potential challenges, and refine technology integration. Predictions: by the end of 2024, successful pilot projects are expected to yield measurable improvements in energy efficiency, with participants reporting a reduction in energy costs by up to 20%. Early adopters may also witness enhanced operational insights, leading to better decision-making processes. 2. Phase 2, Expanded Deployment 2025. Following the pilot projects, the second phase will involve the expansion of the systems to a broader range of facilities. This will include residential areas, public infrastructure, and larger industrial operations. The focus will be on integrating advanced AI analytics tools that can predict energy demand and optimize supply accordingly. Predictions: by mid-2025, the integration of AI-driven analytics is expected to lead to a 30 to 50% decrease in energy consumption during peak demand periods. Utilities may also start to implement dynamic pricing models based on real-time data, promoting energy conservation during high-demand times. 3. Phase 3, Full System Integration late 2025, early 2026. The third phase will involve the full-scale integration of all components of the smart energy systems. This will include IoT devices, AI analytics, and possibly blockchain technology for secure and transparent energy transactions. The goal will be to create a comprehensive energy management ecosystem that can autonomously adjust energy distribution based on real-time data. Predictions: by early 2026. Organizations adopting these comprehensive systems could see a transformative impact on their energy management strategies. It is projected that businesses will experience a 40% reduction in waste and an overall enhancement in energy reliability and security, paving the way for an interconnected smart grid. 4. Phase 4, Continuous Improvement and Scalability 2026 and beyond. In the final phase, the focus will shift to continuous improvement and scalability of the smart energy systems. Feedback from the previous phases will be utilized to enhance system features and performance. Additionally, the emphasis will be on creating a scalable model that can be adapted to different geographical and industrial contexts. Predictions: by the end of 2026, the global adoption of smart energy technologies is expected to expand significantly. Analysts predict that the market for smart energy management solutions will grow at a compound annual growth rate (CAGR) of over 25% through 2030. As organizations realize the benefits of enhanced efficiency and reduced costs, more sectors will likely adopt similar technologies, leading to widespread sustainability practices. Common key points: synergy of IoT and AI. The combination of IoT devices and AI analytics is crucial for enabling predictive maintenance, automated energy distribution, and real-time monitoring of energy consumption. This synergy will allow for more responsive and adaptable energy systems. Focus on efficiency. The overarching theme of the initiative is energy efficiency. As organizations increasingly adopt smart technologies, the potential for significant reductions in operational costs and environmental impact becomes more apparent. Conclusion: the Smart Energy Systems Initiative, projected to culminate by 2026, signifies a pivotal shift in how energy is managed across various sectors. With a strategic investment of $5 million, the phased approach offers a blueprint for successful implementation. If predictions hold true, the integration of IoT and AI technologies will not only enhance energy efficiency but will also catalyze broader adoption of sustainable practices, paving the way for a more resilient and interconnected energy landscape. As we move toward this future, organizations that prioritize these innovations will position themselves at the forefront of the energy transition.